Typically, Firefighter 1 begins with history, safety, communications, and building construction. But you've got to wonder, safety from what? What are we supposed to be communicating about? And how is the building going to react under fire load if we don't know what the fire is about? That's why I believe that the first thing that we should be teaching in Firefighter 1 is fire behavior. So, why fire behavior? Well, it's the foundational concept of what we do. The science of fire is what gets firefighters hurt and killed every year in structural fires. It's what gets firefighters sick from occupational cancers and other diseases. And it's also what kills hundreds of civilians each year in structural fires. Our ability to interrupt the spread of fire attack, and mitigate the hazards of smoke and heat, ventilation, is what makes or breaks any fire service organization in its mission to protect life, search and rescue, and property, salvage and overhaul. I don't expect you to master all of the concepts of firefighting just from this video series. My goal is to simply give you a very basic understanding in order to be able to function, but also to act as a review. Now, I expect you to listen to your instructors and to read your textbook for more information. When I was at Oklahoma State in 2006, I had a professor that, in not so many words, said that the science of fire, studying actual fire behavior, was kind of pointless for engineers who were designing a system that was meant to make that pointless. That never really sat right with me for a couple of reasons. The first one is that it's essential for fire protection engineers to understand the science of fire in order to design a system that fits the very hazard that they're trying to protect, and that someday a fire will challenge it. But also, from a firefighting standpoint, not every home or business has a fire protection system, and firefighters, from the fire service perspective, we don't get to choose what building we go to. Before we can talk about what we're going to do or what the building's going to do, we first need to talk about what the fire's doing.
The fire tetrahedron is used as a visual representation of the flaming or gas phase combustion process. It is composed of 4 parts: fuel, an oxidizer, heat, and a self-sustaining chemical chain reaction. All 4 elements must be in place in order to cause burning, and inhibiting one will stop the process. Fuel is anything that has mass, be it a solid or a liquid, and can undergo a physical change. But solids and liquids don't burn, not directly. Only gases can burn. And this leads to our second component, heat. Heat is what typically causes a state change in matter from a solid or a liquid into a gas, generally through pyrolysis, or heating to a point of thermal decomposition, where the mass begins to break down into combustible gases. In the case of liquids like diesel, kerosene, or gasoline, the action that creates flammable gases is through vaporization and is dependent upon the liquid's vapor density. You can see this when you're filling up a piece of power equipment or a car with fuel and you spill some on the ground or the floor and return later and the puddle is gone. Some liquids have a vapor density high enough that they will not readily convert to a gas from a liquid state. Motor oil is an example. Whether through pyrolysis or vaporization, the mass readily converts to a ready and available state to support combustion at the right concentration, and we'll go over that more at a later time. But we are missing a component: oxygen. Oxygen is all around us. Our bodies can't function properly without a certain percentage in the air we breathe, about 20.9%, but we'll round up to 21 just to make it easier to remember. The rest of the ambient air in our atmosphere is made up of 78% nitrogen and 1% argon, with trace amounts of other gases mixed in. Oxygen acts as an oxidizer, that's easy to remember, that reacts with the fuel gas created by thermal decomposition or vaporization to enable it to burn. During heating, the fuel gas loses electrons, and oxygen readily accepts these electrons and forms new compounds. Oxygen isn't the only oxidizer, and there are many compounds that release oxygen or other gases during thermal decomposition that support combustion. More about those later. Oxygen also drives the final component of the fire tetrahedron, the self-sustaining chemical chain reaction. At high temperatures, oxygen breaks apart into highly reactive oxygen-free radicals, attacking the fuel and generating more highly reactive particles. This chain reaction breaks down the fuel at a faster rate, feeding the continuous generation of heat and driving the combustion process. Combustion produces new substances and compounds, not simply heat and smoke. Heat is dangerous on its own, but smoke and a lack of oxygen caused by combustion cause most fire deaths. Smoke is an aerosol that is composed of various gases, vapors, and solid particulates. Incomplete combustion results in unburned fuel released into smoke. Generally, combustion in a confined space, such as a structure, is incomplete. This occurs for many reasons, but mostly because of a lack of available oxygen and results in fuel gases being entrained into the thermal column. Remember that hot air rises and cool air descends. Smoke itself becomes a fuel as a result, and if oxygen is introduced, it will ignite, sometimes violently. Some of the chemical compounds that end up in smoke include carbon monoxide, hydrogen cyanide, and carbon dioxide. Irritants such as hydrogen chloride, formaldehyde, and acrolein, along with more than 20 others, are also in the smoke suspension. That concludes the first video in the Basic Firemanship series, a very basic overview of the combustion process. In the next video, we will cover fire development in a space, the flow path, and violent fire events.